recording. All right, and so hi everyone. So today we're very excited to have Nikhil Garg as our speaker. So Nikhil right now is an assistant professor of operations research at Cornell Tech. And so his research has been, in the application of algorithms, of data science, of mechanism design, to the study of democracy, markets, and societal systems. And so he got his PhD from Stanford, and he also spent a lot of time in industry. So like more recently, he was the principal data scientist at PredictWise, which provides election analytics for political campaigns. He also received the Informs Danzig Dissertation Award and an honorable mention at the ACM SIGECOMM Dissertation Award. And so today he's going to tell us about his work on auditing and designing for equity in resident crowdsourcing. So yeah, take it away, Nikhil. It's all you now.
Yeah, thanks for having me. So I guess I have to do a sort of a pre-apology. This is more empirical than, it's more modeling plus empirical than modeling plus theory. But sort of, as sort of the type of work that I like to do and sort of I hope to convince you of is, some of I think some of you are very much in this vein, and then hopefully the students to convince you of that sort of doing empirical work first is a great way to figure out what are the right theory problems to solve. And so what I'll sort of, compared to when I usually give this talk to sort of maybe more empirical bent audiences, data science audiences, I'll maybe skip through some of like the nitty-gritty empiric stuff and sort of hope to spend some time at the end on what I think are interesting modeling and theoretical questions that come out of this, some that I'm working on, some that I'm sort of excited to work on in the future if I can convince any of you to be excited as well. So with that, yeah, and so I think, and also most of the talk is going to be on sort of this like current work, sort of the work that's already out, which is going to be on how do we audit reporting behavior in 311 crowdsourcing systems, but then I'll talk a little bit about more of the operation, sort of active intervention piece. And I think that also relates to some of the theoretical things that people like Juba have thought about, like pipeline interventions. Okay, so what's the background? The background is many cities have a phone number that you can call or like an app that you can use to complain to the local government. In the US, this is usually the number is usually 311, and you use it to like, 911 is in the US, you need an ambulance or police officer like right now. 311 is you need the local government to fix something in the next few weeks or month or like the next day or something. So like, pothole, bed bugs, a tree is about to fall down in a power line, those sorts of issues. And these sorts of systems are like absolutely huge. So New York system received about 2.7 million requests last year. And like not only are they huge number-wise, but they're also quite important. So for many types of problems, this is the primary way that the government learns about these problems. So for example, New York has about 700,000, New York City has about 700,000 trees on the street. This is not counting trees in Central Park or other parks, just trees lining streets. And it's essentially impossible to monitor all of them in real time. Sort of there's no amount of funding that you could give to the Parks Department to sort of do surveillance on the entire city for these problems. And so they essentially rely on residents reporting issues about trees that are going on. And this applies to essentially every government agency. And so what's the pipeline of like things getting done? At some point, let's say, an incident happens. So like a branch falls off, it's about to hit a power line, it, starts cracking the sidewalk, all sorts, a pothole appears, like the incident happens. And then at some point later, there's going to be a 311 report generated either a 311 report generated by, I'm going to call them residents, but just some person is going to submit a report. And so, for example, in the forestry subunit of the Department of Parks and Recreation that we've been working with, they receive about 70 to 100,000 reports a year. And then about sort of about 60% of the time, 65% of the time, something like that, of someone physically, the Parks Department assigns a forester to physically go to the location of the report and to like inspect what's going on. So they'll like be like, okay, so what is, they'll actually do an inspection. How risky is this? And so on. And about half the time that an inspector goes out and does a report, that actually generates a work order. Well, the inspector will say, we need a work crew, a maintenance crew to come out here and actually fix the issue that the report identified or that I identified in my inspection. And so the research agenda that I've been working on sort of started on this year is how do we think about auditing and improving this entire pipeline's efficiency and equity, right? So you can imagine there's a whole bunch of places where either inefficient, they're making the wrong decisions of what to inspect or what to work on, or they're making decisions that maybe correlate with space or neighborhoods in a way not sort of justified by the underlying sort of ground truth. Today, I'm gonna 90% of the talk is gonna focus on just one piece of the pipeline. So how do we understand this first part of when an incident occurs to when a 311 report is generated? So how do we understand sort of when that report happens, what's the delay, and so on? And in particular, we're going to try to understand heterogeneous reporting behavior, or what I'm going to call underreporting, which is compared to sort of take two neighborhoods. One neighborhood is going to report fewer problems conditional on the same problems occurring. And why does this matter? Because that's the first stage of the pipeline, right? So if there's disparities in who reports problems and when they report problems, then that's going to sort of, even if downstream everything is perfect, that's going to propagate into downstream disparities in what work is done. Any thoughts or questions so far? Okay. And so what we want to do is we're going to try to measure this underreporting empirically. But we immediately run into a statistical question, which is how do we distinguish between underreporting and some neighborhoods truly having fewer problems, right? So what I told you on the first slide is that these systems exist because we don't observe data, we have no way to monitor all 700,000 trees unless people report them. And so that means us as researchers don't observe ground truth incidents, we only observe reports. And so maybe another way to say this is if a tree falls down in a forest and no one's there to report it, then the city doesn't know about it. Okay, so I'm going to give you maybe one potential approach to get around this issue between distinguishing ground truth and sort of reporting behavior. This is not what we end up doing, and I want to sort of contrast our approach with this approach. So one approach could be, this is maybe the black box machine learning approach, which is use ground truth data on the incident rate. Or try to construct this ground truth data on the incident rate, maybe through some machine learning methods. So how many incidents of each type, hazards, root issues, tree pruning, of all of these types, do we expect to see in each neighborhood? And there's multiple ways that you could try to construct an estimate of this thing. You can physically go out and walk the streets and get a snapshot uncensored view. You could you can use that as training data for proxy methods, right? So you could count the number of trees on each street. You can look at their size, you can look at their species, you can look at all sorts of other administrative data you have and sort of use that as predictors, and then sort of in your walk of the street, sort of use that as the training data. I'm going to claim that this is really hard to do, right? Or I'm not going to sort of talk about doing it in this work, but sort of you have many different types. You're going out and walking the streets might actually be really expensive. And even if you can do all of this well, you're only going to get a count of the number of incidents that you might expect. You're not going to get a count of or like any data on when these incidents occurred. So you're not going to get a count of, this tree was about to fall down a week ago versus it happened yesterday. Okay. And so the question in this work, the methodological question is can we measure this sort of underreporting or more generally heterogeneous reporting without any notion of ground truth data? And the key idea where there's been a lot of theoretical work in this recently, actually by a lot of folks out of Stanford. So the PhD student, Kieran, and I think he's an MSNE, working with Moses and a few others, have sort of made progress on this literature called the missing species literature, which is sort of in the classical formulation, you have some distribution, you've observed histograms of counts, you've observed some count distribution from this, some histogram from this distribution, and now you want to estimate the support of the distribution. And so the key idea from that literature is you want to leverage the sort of the histogram information beyond just the support of the histogram you observe. So leverage the rate of duplicate reports you observe about the same incident to identify reporting rates conditional on incidents having occurred. And I'll formalize this in the model in a little bit. And so first, and our setting has a few other complications because now time is a factor where incidents are born and then they die. But sort of that the core idea is the same as this missing species literature. And so what I'm going to talk through today is first just like walking through the statistical method in the model, and then applying the method to audit reporting behavior of street tree incidents in New York over 3 years. Any other thoughts or questions so far?
Can you motivate why it's called like the missing species method?
Yeah, so sort of it started by, or maybe this is more apocryphal, but sort of one of the starting motivations was, suppose a biologist is walking around a forest and they walk around for 1 week and they observe 10 species. And then the question is if they walk around for 1 more week, how many new species would they observe? So you want some estimate of the species of the number of species you haven't observed yet. Any other thoughts or questions? Okay. I'm gonna sort of, for time purposes, sort of like just skim through the related literatures. We're not the first people to think about 311 systems and sort of what are called co-production systems. A lot of, especially political scientists, administrative, sort of some in the social sciences have thought about this and have primarily used this like proxy ground truth method that I talked about. I think there's a phone number I can give you, Juba, sort of for the polar bear. And then sort of methodologically, like we just talked about, this is closer to what a lot of people in ecology sort of try to do, where they have two highly related questions. The first one, which is this missing species question, which is how many species haven't you seen yet that exist? And then the second one is sort of given a species that exists, what is the population of that species, perhaps distributed across space? And how do you actually do that counting? Okay, so let's go through the model. So I'm going to have an incident type theta. And the way to think about theta is that it should encode both geography, so like the neighborhood that this incident happened in, but also incident type characteristics. So is it a hazard? How big is the tree? Is it about, is it cracking the sidewalk, or is it about to fall down in a power line, or so on? And then I'm gonna say that an incident I of type theta is going to occur according to some arbitrary process, big lambda of theta. And let's say that it occurs starting at time ti. And I want to make 0 assumptions about this process, big lambda of theta. So it doesn't have to be Poisson or anything. But sort of given that an incident I has occurred of type theta, we're going to say that people report that incident according to a Poisson process with rate lambda of theta. In the modeling section, I'm not going to sort of make any assumptions about little lambda of theta being an homogeneous Poisson process. It's just some Poisson process parameterized by some potential function lambda of theta. In the empirics, of course, we're going to start needing to make more assumptions on lambda of theta in order to sort of have a tractable estimation. Okay, so so the incident occurred at time ti, which is unobserved, and then at some later time, according to the process little lambda of theta, we're gonna receive the first report about the incident, and this is the first time that the department or us as researchers know that the problem exists. Right, everything before this is unknown, and then things continue to happen, and maybe at some point we're going to receive a second report, and at some point we might receive a third report. At some point, the incident might also be inspected by the Parks Department, right? So the Parks Department is going to be looking at these reports, and potentially as a function of both the reporting type and the number of reports, it's going to decide when to inspect the thing. And that's going to be logged in the administrative data, and so we observe when it got inspected. And then at some point, I'm going to say it's unknown, and I'll explain in a little bit. So at some unknown point, which is capital TI after the incident occurred, the incident is going to die, right? And so when I say die, I mean it's maybe fixed by the agency, at which point it would be observed timestamp because we have it in the data. But it could, it could have just the branch could have washed away, or some neighborhood Good Samaritan could have fixed it up, could have fixed it, or whatever, right? So yeah, it could die for all sorts of reasons, and I don't observe all of them, so I'm just going to pretend that TI is unobserved. Okay. Any questions on the process, on the data generating process? Okay. And so what's our research question? Our research question is, how does this reporting type, how does the reporting process little lambda of theta depend on the type theta? And so why is this potentially a useful question, or a question we care about? The first one is little lambda of theta directly gives us a sense of the reporting delay, right? So if you had an homogeneous Poisson process, then the reporting delay defined by the time between the incident occurring and the agency knowing the incident exists is approximately 1 over lambda of theta, right? Or it's a random variable with mean 1 over lambda theta. And that's going to now be a lower bound in the the delay it takes for the Parks Department to inspect the thing and to fix the thing. Some incidents may never be reported if they have a low enough reporting rate, right? So if things naturally resolve either for good or bad, or if the tree dies or something before it gets reported, then that's a bad outcome.
Can I ask a question that I don't quite understand? Is there some notion of costs or limited resources with the agency? If it's cheap for me to respond to the trees, why don't I just immediately jump when I get the report? There's no false reporting, right?
Yeah, that's a great question. And so that's what we're actually working on now. And so I'll show you in a little bit histograms of how long it takes for them to inspect things. And there's an incredibly long tail. So a lot of things get inspected within a few days. But then there's some things that don't get inspected for hundreds of days.
Okay, so this is the first kind of baseline, and then
yeah, right. So this project is just trying to find out that first stage of the pipeline, and you can think about there's delays, there's capacity constraints on each stage of the pipeline, and you could think about intervening at different stages. You can think about auditing each stage by itself or all together, and I think that's where the exciting future work is. That hopefully I'll motivate a little bit at the But yeah, I think you're exactly right. Sort of maybe a more aggressive version of your question is maybe this like this reporting delay doesn't matter because everything is going to take 200 days to get inspected anyway. And so like, it doesn't matter if the reporting delay is 1 day versus 1 week, if everything is going to be, if like there's like orders of magnitude higher delays down the road. I don't think that's true, but sort of that like nothing I've shown you so far like sort of proves that that's not true. Yeah, okay. And then any other thoughts or questions so far? Okay. And so I just want to point out that like it's not necessarily a bad thing that the reporting rate is heterogeneous in the type data, right? So like we do want more dangerous incidents to be reported more, right? Like I do want something about to fall down on, like if a giant tree is about to fall down on a power line, I do want that reported immediately. Whereas if like, you know, a tree is like cracking the sidewalk and it's gonna like cause a little bit of damage, but it's not like about to kill anyone, then like I don't actually care if it gets reported immediately or like 2 months later, right? And so some of this heterogeneity by type is like expected, and like it's like we don't particularly care about it in a negative way. On the other hand, sort of there is a concern, and what I hope you would agree is that spatial heterogeneity is probably a bad thing, right? So if conditional on incident characteristics, one neighborhood is reporting at more delays or is just reporting fewer incidents, then they're going to get worse government services, and that's probably a bad thing, right? So so you know, we would want to measure this, and we would want to potentially counteract it in downstream parts of the pipeline. Okay, so I'm going to skip the naive method, but sort of what I just have on this slide is just like a naive observation, which if the only thing that you did was count the number of unique incidents reported of each type in each location, then you don't have identifiability, right? So like if all I did was count, you know, this neighborhood has 20 incidents reported, that neighborhood has 100 incidents reported, then like I can't distinguish between incident rates and reporting rates, right? Because you don't know sort of, you can't distinguish between those two things. And so what's like kind of surprising to us was like 90% of this literature and like the 311 literature going back to like the 80s ignores this, basically does like this naive method, which like on the face of it just doesn't work. Right, is like just like counts the number of incidents reported or the total number of reports and then compares them across space. Some recent work, which I think is actually very good work, but you know, it might be hard to do, is they find proxies for this incident rate lambda theta and then normalize by that and get the reporting rate that, and so try to distinguish between reporting rates that way. Okay. And so what's our method? The first insight, the first thing that we do is just, you know, is just the following insight, which is the same from the missing species, or similar from the missing species data literature, which is that duplicate reports about observed incidents give us the reporting rate conditional on the incident having occurred. So like, what's the intuition for this? Let's pretend that I actually observed. First of all, let's pretend I observed every incident, and for every incident that I observed, I observed exactly when it happened and exactly when it died, right? So suppose I have perfect like video surveillance of the entire city. Then to get little lambda theta, sort of to understand the reporting behavior, that's just Poisson distributed with time duration capital Ti. Right? So if I know this entire reporting duration capital Ti, then this problem is just a very simple Poisson regression Poisson rate estimation problem. right? There's no research to be done here, at least methodologically. The issue is that we don't actually observe this interval TI, right? We don't observe this beginning interval between birth and the first report. And we don't observe this end interval between the last report and the death. So we don't actually know the Poisson time duration TI under which we could do this Poisson estimation, rate estimation. And so the second insight, or the second task, is how can we construct an interval within which the number of reports is still distributed according to a Poisson random variable, but that the endpoints of the interval are observed, right? So I need to construct an interval AB within which reports are Poisson. And so the following theorem, this is not like, nothing like groundbreaking. This is purely a translational theorem. And I'll explain how it connects to memoryless property in a little bit. But just sort of, we need the following. We need potentially, quite obviously, we need A and B to be within the birth and the death, right? So we need the start of the interval that I count after the incident happens and before the interval goes away, right? Otherwise, I'm including time periods in which no report could have happened. I also need A and B to be stopping times. And so what do I mean by stopping times? I think it's important to get the precise definition here correct, which is we need conditional on the events up to that time. So, for picking a point B, we can use the fact that there's 3 reports up to then. But so conditional on the sample path up to that time, these points are not dependent on the future. So they're not a function, B is not a function of anything that happens after B. And they're independent of the reporting rate. So they're independent of the reporting rate, conditional on the number of reports so far, right? So you can have dependence through the number of reports, but you can't have dependence conditionally. And so, why am I making a big deal of this? Is because a lot of naive things that you might want to do to construct this interval don't actually meet these criteria. And so things that we tried at the beginning and then quickly realized they don't work. And so what's the first naive thing that okay, so actually before I get to things that don't work, let's just think about the first observation is the best, the unambiguous, there's not a good argument otherwise. Choice for A is the time of the first report, right? So you want to start your Poisson interval at the time that the first report happens, because that's the first time the incident exists, birth happened before that, and it's a stopping time, right? Because it depends on an event that happened at A, but it doesn't depend on anything after that time, right? So I'm going to start my interval at the first report, but then I'm not going to include the first report in my in the count, in the Poisson count. And so what about B? How do I end the interval? The first naive thing you might want to do is just do a fixed duration fixed duration T, right? So just say 10 days after the first report, I'm going to count count the number of reports that happened between the first report and 10 days later. The problem is, and this relates to Kevin's question earlier, which is there's a very heavy tail on how long incidents are alive. And so this is just a distribution of how long it takes for incidents to be reported, but alive, or how long it takes for them to be inspected. But how long they're alive, or work orders are done, would follow a similar distribution. And so a lot of things are inspected within a few days of the incident happening, and especially hazards. But then some things are not inspected or resolved until 200 days later. And so if you fix any time T, then if you fix it T as 2 days, then you're throwing away a lot of data for like the unimportant things. And you're basically gonna like estimate 0 reporting rates for those things. But if you pick something like t equals 15 days, then you're actually gonna be biased and underestimate your reporting for like hazards, because like those already got fixed 15 days later. And so of course you're not gonna see reports. What's the second thing that you could do naively, which is just the time of the last report, right? So just say at some point this got reported for the last time, and that's going to happen before death. And so just use that and then count the number of reports between the first report and the last report. The issue is that's not a stopping time, right? So by knowing the fact that it's the last report, I'm using information from the future that there were no more reports. And so maybe qualitatively what I'm doing is I'm systematically removing times in which the incident was alive, but which no reports were generated. And so that leads to underestimates of my estimates. What we end up doing is we take the minimum of some fixed interval t, and we can vary this and sort of empirically, and it doesn't really change things. So we take the minimum of some fixed number t and the time it takes for the parts department to inspect it, right? So with the idea that by the time they inspected it, like the vast majority of the time the incident is still alive, and it like naturally adapts to like the severity of the incident. And this ends up being sort of, and it's a stopping time, right? So like, the parks department doesn't have a way to tell the future. And so if they're making a decision, it has to only be dependent on the past. And so what the method ends up being very simple. For each incident I, just construct this interval and count the number of reports inside the interval. Then the number of reports is Poisson inside this interval. And so, for example, if we empirically want to do an estimate a homogeneous Poisson process, then the number of reports of I is distributed according to a Poisson of lambda I times the length of the interval. But the same exact process will end up working for any sort of inhomogeneous estimation that you might want to do. For example, we end up also doing what's called zero inflated Poisson, which is after the first report, you flip a coin and say, I'm not going to, if the coin flip goes heads, I'm not going to have any more reports. If the coin flip goes tails, then I'll get more reports. Any thoughts or questions about sort of the method so far?
I have one question I probably should have asked earlier, which is how is like population density accounted for? Like at what part of like the modeling is that sort of considered? Yeah,
that's a great question. So I'll get to that in a little bit, but eventually, so actually, I think it might just be on the next slide.
Oh, okay.
Yeah, okay. So not exactly that, but something that'll help me answer that question is on this slide. Okay. So like, what do we end up doing? So this method so far is like, a theoretical method that, this gives me identification. But like, how do we implement this empirically in the data, right? So we end up doing Bayesian regression in a programming language called Stan, which allows you to just like code up across the like sort of estimation like this. And we end up doing sort of Poisson regression in the following way. We say that the reporting rate lambda of theta is a function of, there's some intercept, but then a function of like, sort of coefficients on the dimensions of the type. And so the dimensions of the type here could be like the height of the tree, how risky, like the category of the report, what the inspector said on how risky the report is. But then sort of the dimensions of the type could also be like spatial characteristics. So like, for example, the type theta can contain an indicator for each census tract, like the census tract of the incident, because we have latitude, longitude, which we can map back to census tract, right? And so you can do indicators for census tracts, or like you suggested, you can convert each census tract to sort of its like coefficient, it's like, its characteristics like density, ethnicity, education, all sorts of things, include that in the type instead. But sort of in the main analysis, we end up including this type, an indicator for the census tract. But that ends up being super high dimensional, right? We have an indicator where there's over 2,000, like it's in a 2,000 sort of dimension sort of category. And but we end up sort of using what are called spatial smoothing models, which is you constrain each coefficient for a census tract to be drawn from the mean of its neighbors. So you say that each census tract needs to be similar to its neighboring census tract in reporting rates, or you penalize it for being different in your estimation. I'm happy to talk about this more in detail later, or now if y'all want. But sort of maybe when I show pictures, it'll be a little obvious. Okay. But yeah, any other questions on the method before I apply it to the actual data? And I think I'm gonna like breeze through the data application, because I do, for this audience, want to get to what I think are interesting theoretical and modeling questions. Okay. Yeah, so very quickly, we're using mostly public data, but the Parks Department also gave us internal data on inspections and anonymized caller information. We have about 100,000 unique incidents inspected, corresponding to about 140,000 service requests for those inspected incidents. And then the incident covariates are, like I said, location, reported characteristics, inspector report. I'm going to skip through. So there's a few ways that the data doesn't match the model that I presented. We don't think they're a big deal. I'm happy to talk about this offline. And so some summary statistics, sort of this first one is just the plot that I had earlier, but just now the cap at 100 days, which is there's a heavy tail for how long it takes for something to be inspected. And then, but also sort of the number of duplicate reports you see in this time window is actually almost exactly what you would expect with the Poisson distribution, except for, in a Poisson distribution on a log scale, you expect a linear decrease. There's some weirdness at the beginning, whereas it's zero inflated, but then sort of there's fewer ones than you would expect. But then otherwise there's it's nicely Poisson. There's some evidence that it's actually fairly homogeneous. Like, I was really surprised by looking at this plot. I'm happy to talk about it offline, but it's, the reporting rates are actually fairly homogeneous. Okay, so high level result number one, which is like more of an efficiency result, which is, and validates the method, which is, we do find that reporting rates are much higher for more urgent incidents. So if the first caller said that something was a hazard, compared to something they said it was like a pruning request or a request to remove a tree, the reporting rate ends up being like sort of 3 to 7 times higher for hazards than there are for other things. If the inspector said it was risky, then you also see a higher sort of reporting rate. If the inspector said the tree was in excellent condition or fair condition compared to critical or sort of poor condition, you see lower reporting rates, right? So this is almost exactly what you would expect, where like things that matter more are reported at higher rates. Unfortunately, you also see wide spatial disparities that are on the same order as the incident level characteristics. So this is sort of the census tract coefficients from that spatial smoothing model, where I have 1 coefficient per census tract in New York City. And you see that sort of like parts of Queens and Brooklyn sort of have 3 to 7 times lower reporting rates than, for example, parts of Manhattan. And then you can do all sorts of things like, okay, you can correlate these with census, you can regress these against census tract or census, variables like density and so on. And you do end up finding that exactly like you might expect, sort of lower density places report sort of at lower rates, but also sort of poorer neighborhoods, neighborhoods with lower average incomes, lower average education levels also report at lower rates. And I just want to point out that these sort of spatial disparities are on the same order as the incident level differences. And so there is wide and like sort of substantial inequities here in reporting rates. Okay. And then sort of, I don't know about you, but at least I don't think about things in terms of like lambda coefficients in a regression. And so let's just like make this very concrete in what it means for reporting delays. So if I have like a hazard, like the worst possible type of incident, like it's hazardous, it's a tree in poor condition, the inspector after inspection marks it as high risk, then our coefficients imply that in Manhattan, you would expect to sort of see, I was just making sure that these are the updated correct numbers. Yeah, so in Manhattan, you would expect to see the first report about 2.5 days after the incident happened. On average, in Queens, you would expect to see it about 4.7 days later. And this is just average across the boroughs. So this is not taking like the highest census tract and the lowest census tract. This is like averages across boroughs. Whereas like something like a medium risk incident, so like there's some tree damage, it's in poor condition, but it's maybe not like high risk. In Manhattan, on average, 15 days, in Queens, on average, 28 days. And then for like the least significant type of incident, so like a root sewer issue, like it's, it's cracking the sidewalk or something, the tree is in mostly good condition, then sort of reporting delays are on the order of hundreds of days. And these are just directly sort of like taken from the regression table I showed you a few slides ago, and then like turn it into days. Okay, so that's all I had for the empirical results. Are there any questions or thoughts so far?
I don't know if you, yeah, maybe this is something where you don't actually have your data. Maybe you said this, but like, is there? I could imagine another thing you might see is a correlation between like reporting delay and the amount of time that it takes for an incident to be resolved afterwards, right? You're just like sort of thinking, okay, if it takes a long time, if it takes a long time for things to be resolved, I'm less likely to report them because I'm not getting feedback, right? Like I'm not incentivized to report. Is that the case? And also, I guess, it seems like this will also affect, like, I don't know if there are cases where like certain kinds of incidents where you can't actually get a good estimate of reporting rate because reports are so infrequent. I don't know, I guess, yeah.
Yeah, no, those are great questions. So the first question is like, sort of, I guess I view that as like a causal question of like, what is causing lower reporting, sort of like in different neighborhoods. And there's some work on this. I'm gonna mess up the name. I wanna say Buell, Chris Buell, but I could be completely wrong. I'm happy to find it. But it's just sort of this person out of Harvard sort of looking at sort of, I think he did an intervention where sort of increased the operational transparency of like sort of like some sort of dashboard, like, your thing is getting fixed, or like, here's when it's scheduled and so on, and found that increased reporting rates, right? So like transparent government leads to like more people reporting. And like definitely people in political science sort of have done all sorts of things, like sort of like theorize that, trust in government, like sort of like not just like access issues, but like trust in government and historical service and so on affects reporting rates. So that's like certainly like in like all there in the backdrop. It's like in methods like this, it's really hard to do any sort of causal identification for like what's causing these disparities. Like I don't want to claim anything, like, even though like the coefficients do end up correlating with education and ethnicity and like all sorts of things, density, I like absolutely do not want to, like, we do nothing causal here, right? It's like we have no reason why, like we don't know why those neighborhoods have lower reporting rates. And then on your second question of like, it's like sort of data issues, and like that's definitely is happening sort of for a plot like this, right? There's 2,000 census tracts. there's certainly census tracts that have very few trees, very few reports, both randomly and for all sorts of reasons. And that's why we do the spatial smoothing. So basically, sort of we impose in the estimation that like the census, sort of the coefficient right here for this census tract is like sort of related to the coefficients in nearby census tracts. And sort of what that'll lead to sort of in the model is if let's say one census tract has absolutely no data, right? There's like 0 incidents reported for that census tract, then the coefficient for that will just be the mean of all the neighboring census tracts. But if a census tract has a lot of data, then it could sort of deviate far from that prior. Yeah, so great question, and we definitely need to do that sort of in the actual estimation.
Thanks.
Okay. Any other questions about sort of the work so far, the empirical results, the methods, the model? Okay. So yeah, I want to move on, especially for this audience, maybe in the last 10 minutes, to sort of talk about what I think are some interesting modeling and theoretical questions, some of which that we're working on, but sort of most of which that we're not. So sort of if folks are interested, please reach out. The first one is, I think the sort of the, partially because the algorithmic fairness community is coming mostly from machine learning as opposed to operations. But I think there's a big lack of thinking about fairness in pipeline systems where like time matters, right? So like, so we have a system here where, you know, some incident happens, sometime later, the incident gets reported, sometime later it gets inspected, and then sometime later it gets fixed. And like the ultimate objective is like, one way to think about the objective is like latency of of incident to fixing, like that entire sum of time. Or you could think about like how that maps to like ground truth outcomes, right? So like the longer the delay is, the more likely that tree is to like actually fall down and cause damage, right? But just like sort of notions of like, how do we think about auditing sort of some such pipeline systems where you have different stages and sort of like, what are the right fairness notions, but then what are the right sort of like, you know, this would be like an extension or sort of related to like Juba's work in pipeline interventions, right? So like now we have capacity, and this relates to Kevin's question earlier on, which is we have, you know, capacity constraints over time in each stage. How do we best compensate for delays in prior or future stages, right? When we're doing like scheduling of inspections or scheduling of work orders. We're working on this auditing piece right now, but sort of we're working on some intervention piece, but we're not thinking, so far we haven't been thinking about this like end-to-end intervention piece as opposed to just like one level intervention. And then the second super high level question, and this is actually what made me super excited about this and sort of going down this direction in the first place, is how do we think about participation in crowdsourced voting systems beyond just like thinking about individual rationality or incentive compatibility, right? So like, what's like a standard mechanism design approach to participation is that an individual participates in a mechanism if like sort of it's individually rational, if like in expectation they get out of it sort of their expected cost. But here it's like not quite that, right? So like here we have participation of groups, you know, for example, neighborhoods as individuals. And then you also have like, you know, like it's unclear if you could put this in like someone doesn't report something in like a cost framework, as opposed to just some like baseline propensity to participate or not participate. And then how do we think about designing the right sort of mechanisms that are like, you know, the mix of like reweighting techniques or statistical techniques or like attempts to equalize participation. And so like, I'll give like a very concrete example. So like, for those of you familiar, you know, I'll give the Stanford example. So in grad school, one of my advisors was Ashish Goyal, and we did a lot of things in participatory budgeting, right? So like actually going out and setting up these systems that a bunch of cities use to vote on a budget, right? So do we spend money on this park or do we spend money on this baseball team or so on? But one like worry, and Ashish has been working on this a lot with more recent students, Like one potential worry is that, who do you expect votes in these off-cycle city elections on a random Tuesday, right? It's like the participation is probably not reflective of the underlying community unless you do, and they often did, right? So like sort of Ashish was really thoughtful here. A lot of the cities that they worked with were super thoughtful here and did a lot of the outreach to try to make sure that participation was like reflected the underlying city. But like oftentimes that's hard, right? Oftentimes it doesn't. So like what are maybe more algorithmic techniques that we can do to sort of, once you have the votes, once you have the data that you have, to try to correct for unequal participation? And then sort of how does that connect to more normative ideals like, you can't just weight some people's votes more, like, that goes against one person, one vote, sort of maybe more like individual fairness notions. And so I think there needs to be a lot more careful thought in what do we do about these crowdsourced and voting systems where the votes don't reflect the underlying society.
Can I ask a question at that point?
Yeah.
Do you have any sense about people like strategically reporting? Like there's an ugly tree on my street, but like I tell the 311 that there's like, it almost fell on like a preschool with like 10 children in it. It's super urgent. And how to think about that in this type of model.
Yeah, that's a good question. Yeah, so like, I mean, everything we did was just, taking the reports at face value. And you can imagine that they're sort of like more generally misreporting is an issue, right? It's like people aren't, and so that's one sort of deviation is like they sort of exaggerate the danger in order to get it inspected and fixed earlier. We haven't looked at that directly yet. That was something we wanted to look at, and sort of there's a lot of work in like, especially in criminal justice, to think about sort of how do you actually like audit things like that in a censored data setting where like, we have censored data and not everything gets inspected and things are getting inspected as a function of what the reporting type is. And so like, you have to be like very careful with how you do the estimation. There is past work in this like political science sort of studying 311 systems that like try to think about misreporting. Frankly, I don't know how much to trust it, given what I know about the literature on underreporting. I've read some of that paper. Some like those papers often confuse misreporting and underreporting, and sort of they use that like things weren't there when they were reported as a measure of underreporting or overreport. So like, I think this is a very complicated question to actually study. I don't know. Yeah, I haven't looked at it myself yet. And I don't know sort of the state of that literature for folks who have looked at it. So maybe I can just do the last slide then. So yeah, so this is my standard last slide. So now we're working on sort of, this was like an auditing piece on one stage of the pipeline. We're now thinking about auditing other stages and like doing more active operations. So can we like, reprioritize inspections to like incorporate these sort of delays and so on. This is mostly being done from an empirical angle. But I definitely think there's a lot of theoretical and modeling work to do. And then the other one is if you all have connections, sort of like, we think the method is fairly general. It doesn't just apply to trees in New York. It applies to all sorts of reporting systems. For example, I think software bug reporting, if any of you have contacts like, I don't know, Microsoft or something, please send them to me. But yeah, that's all I had. Happy to sort of, in the last few minutes, just have a conversation about anything I talked about.
Yeah, thanks a lot, Nikhil, for the great talk. Yeah, so if you have any questions right now, we can maybe take, like 1 or 2 questions, but it's also 1 or 2 already. So, yeah. All right, I'm not seeing any questions right now, and it seems like people may have to run, so maybe we can stop here and stop the recording right now too.
Okay. Well, hope to see everyone around. I'll probably be at